Hello everyone. This is my last project. The project that you see here is STM32 nucleo board connected to a real-time clock, the DS3231. And as you can see here in the serial terminal, I'm just reading the raw data from the real-time clock just to verify that it is working. They are communicating. But the thing or the reason why wanted to show these is because like a month ago I was in the Embedded World North America convention, and I had the opportunity over there to see a lot of cool projects. But one of the projects that caught my attention was this project that basically it's a software or a platform that uh, kind of help generate device drivers, like and the way it works is you upload the data sheet of the device, and AI model will process the data of on the data sheet and will generate the drivers for you. So once you have the drivers, you can integrate them into your project, and it speed up the process a lot. So I want to show you how I'm going to be following the actual guide from the official site, and on their GitHub page. You can see it here. I also will leave the links in the description so you guys can you can easily integrate it using a Nucleo board or any other microcontroller that you have. So I'm gonna walk you through the process. I'm gonna be following this guide, and just gonna modify it a little bit at the end. But so yeah, so I'll start generating the drivers, so the drivers for the RTC, and we'll go from there. So all right, let's generate the drivers. So here we have the Embedd.it website, and here we can do the driver generation using their platform, or you can also install a VS Code extension and log in with your username, and you can also generate it. It's exactly the same. I'm gonna use the web browser and to generate the files. So I'm going to upload the PDF for our DS3231, which is a real-time clock. So once the software or the AI reads the data sheet or process the data sheet, you will see this here, and you will have different or here on the left the tree configuration, and so here you can see the PDF file of the component or the device. And here we have the different options. These are the options by default. I'm going to by default options, use C, bare metal, allocation memory is going to be static, little endian that matches our STM32 microcontrollers. And so here are the different tabs with the information that the software extracted from the datasheet. So her device name and several different options, but the most important for us here is I2C interface, and this 100 kilohertz the baud rate, and that's the addresses that the device can have, 68, 69. We also have here the registers, all the register map extracted from the datasheet, and all the data types also extracted from the datasheet. If you see any errors here, it will have like a small indicator, like a red dot, and also a red indication here on this on the register, where you might have some errors, or the when the software extracted the information from the datasheet, um, and there was an error, it will be indicated, and you can modify these uh, in add register or modify any register. And here in the setup, you can add some registers where you can initialize the value of those register according to the configuration that you need for your specific device. And all we have left here is to actually generate the drivers. So we can come here and select driver, and it's going to start generating drivers. This might take a few minutes, or well, maybe not. It's ready. So here are all the drivers. So I'm going to download these to my downloads folder, and I'm gonna call it like DS3231 drivers. So once we have the drivers downloaded into our system, we're gonna add those files to the STM32 project. So I'm gonna do that, and I'll see you in a few seconds. All right, so now that we have our drivers generated, I'm gonna start creating the project in CubeMX. I also want to include in the project the code that I used in the last video, and but I'm not gonna type everything. I'm gonna try to just copy and paste from my reference project, because I don't want to make this video like very long, and as the previous one. I know that sometimes this can be boring, so I'm just gonna create my project Nucleo 446 actually, and DS or TC DS3231. All right, so I'm gonna include and it's also a way that that you can see how the advantage of having the some custom drivers or libraries for the things that we use like frequently. So I'm gonna modify this a little bit. Let's call this LED, and my system, that is okay. I'm gonna do the bypass. This bypass clock source is gonna use the clock coming from the ST-Link on the integrated in the Nucleo board. GPIO, I want my clock running at maximum frequency, 180 megahertz. That's fine. I'm gonna add a timer for my LED because we are gonna use interrupts for this. Enable the interrupt. And as you can see here, we are gonna use the timer 14, and we have multiple clocks here for the timers. So you need to check the data sheet of your device to verify where is that connected. So I did that for my board, for my microcontroller. And as you can see here, timer 14 is connected to APV1. So APV1 here is running at 90 megahertz. So I'm gonna divide this by 9,000 just to bring the clock down to 10 kilohertz, and another 9,000 here. The explanation why these values you can find in the previous video. You can watch the video, and I know it's long, but I think it at least it adds some value. So basically, we are generating here, and the auto reload is disabled because we are generating the interrupt when we are enabling every time that the interrupt occurs, because we want to create not a typical LED blinking pattern that you have it for on for the same amount of time that is off. So this creates a little bit different pattern that I think it looks nice. So here, so that's configuration for the timer. We are going to also enable the I2C. We need the I2C on these two pins. And I think that's all. Now we can save it, generate a code. So what I'm gonna do now is I'm gonna bring the actual code to blink the LED. So I'm gonna drag this, my custom drivers, I copy the files, refresh here. So I have to include these so the compiler can find the well, files. And also I need to tell the compiler that we have some .h files in that folder. So we're gonna come here, custom drivers, click OK, apply and close, rebuild index. And now the first thing that we need to do is to include our led.h, and we are going to also define here the time where the LED is going to be off for 0.9 seconds, and it's going to be on for 0.1 second. So it's going to create that rapid like flashing of the LED. The other thing that we need to do is initiate or initialize our LED driver, and we can do it after we have initialized our timer. And the timer 14 is the one that we are using. So yeah, and now we need to just define or create our function that to update the LED every time that interrupt occurs. So this function is defined actually in the STM32 Hall drivers, but it's defined as weak, so we can redefine it in our own code. So here, every time that the timer interrupt occurs and is coming from the timer 14, we're gonna update the LED with the time on and the time off that we define it above here. So if we compile these, see if we have any errors. So no errors. So we can basically program our board, and the LED should be flashing now. Let me set the camera so you can see that the LED is actually working. So there you have, that's the LED working. All right, so now that we have the LED working, now we are going to include the drivers of the real-time clock that we generated. And so the drivers are here. We're gonna drag this inside the drivers folder. Just copy those files. And we also have to tell here the compiler that we have some include files in that path and that folder. So here, drivers, here, click OK, OK, apply and close. So according to this, the first thing that we need to do is going to be include our header file. Right, so we have our header file there. And now we need to create a, well, it's already created, or the driver already generated a macro, but we need to call that macro to create the device object for the RTC, or the real-time clock. So we need to create that object, and we're gonna do it here. So that's a macro. So after that, we need to define or create the function prototypes to read and write to the bus, to the I2C bus. And now we need to create the object. They call it the bus object, which is basically acting like a interface between the drivers and our hardware, or the HAL library of the microcontroller generated using the CubeIDE or CubeMX. So we generate that, and now we need to define is or create our functions to read and write and usually I do that at the end after here. So basically in these functions here to write, you're gonna receive that pointer to that structure, to that object, to the device object, to the pointer to the data, and how many or the amount of data that you're gonna write. If everything goes well and those are defined, we are going to fetch the configuration of that device object, and we are going to pass it to our HAL library, where it is going to actually write or read from the RTC. So basically, what the most important thing that we need from that configuration is the address of the device that we are going to define in a few moments, in a few minutes. And the same for the read operation, or for the read function. It works very similar. And the next thing is we need to define, it's also these drivers, they use an internal delay function. Is based on the HAL delay function generated by the CubeMX. And so now we need to define the address or of the real-time clock. So we're gonna do it here on our private definitions, and remember, you always use these guards whenever you create your code, so if you need to regenerate the code, it doesn't get deleted by Cube IDE. And we are going to also create create the association between the drivers generated by the embed and the drivers generated by CubeMX or Cube IDE. I'm gonna do that after all the initialization. All right, so here on the device object, in the boss of the device object, we are going to assign this interface that also connects to the functions to read and write to the RTC. So once we have that, well, let's save these. We can compile, see if we have any errors. All right, so everything's good so far. So here's where I'm going to modify it a little bit, the actual code of the guide. It's just because I don't want to read all the registers on the RTC, just to read hours, minutes, and seconds. I think that's enough to prove that it is working. So for that, I'm gonna come here. I'm gonna bring this. I don't want you to see me like typing all of these, because it's gonna get very long and very boring. It's already boring. All right, so I'm gonna create here some variables to hold the values that we are going to read from the RTC, and these functions, these are generated by the embed, and but basically we're passing the device object, the register address that is also generated by the embed, and the variable where we want to save the data read from the RTC. If everything goes okay, I'm going to send this using the UART. I'm gonna send that to the console. So we can write, if for some reason we have errors, we're gonna send this error message that I also need to define, that I haven't done. Where it is. All right. All right. So I'm gonna create that error message, and also I'm creating here the buffer to save the string character that we are going to send to the console. See if we compile, We should be fine. We have a couple of warnings. Printf. Oh, because I didn't include. I forgot to include that stdio.h. Compile again. All right, so the warning is gone. So it should be fine. So now we can debug. Just clear this. Clear the buffer. All right, if we now hit run, it's gonna start displaying some data. So here we can see that it's incremented approximately every 5 seconds because that's the delay that we or I added here. You can do it, I don't know, more often or even at 1 second. You can play with that. This is only to demonstrate that it is actually working. So as you can see, the Embed software help us a lot just to generate the drivers that speed up a lot the process of developing or using different modules. So right now this is now very early in the development. When I talked to the developer in the embedded world, North America, that was in Austin like a month ago, he told me like so far there's only supporting I2C and SPI to generate drivers for generating drivers, but they are planning to expand to another standards and protocols. And so far they have only two type of membership, which is the free one, which is the one that I have and been using. Is it's limited, but so far it's been okay. And the enterprise, I think, is the other one. I'm not really sure, but yeah, you can create sign up for a free account and try it for yourself, and see if you can, you could see that it actually helps to develop. As I said, this is still in early. It's a very young company. I think it's based in the UK. Um, but I think it has a lot of potential if this improves and include other type of standards like UART or Canvas. It can, I would say it can grow a lot. And well, check that out, guys. And let me know in the comments if you want to see something else generating drivers using embed, and see if we can make another cool project and verify that it works. Thank you for watching, and I hope this video is not too long and not too boring. Thank you so much for watching, and I'll see you next time.